Hi, and welcome back to our review for Chem 4. We're doing our first example ever where we determine the pH of a salt. And the question is this: what's the pH of a 0.085 molar NaBrO solution? As always with pH, we ask ourselves two questions. Is the compound an acid, base, or salt? It doesn't have the acid hydrogen, so it's not an acid. It doesn't have the OH, it's not a base. So this is going to be our first salt problem. Now let's look at the salt, NaBrO. Metals, like sodium, anything to the right of the staircase, metals never set the pH. So I'm going to cross that out, and we're going to look at our conjugate. Since it's a negative charge on this conjugate, we know that this is a conjugate base. So what was the original acid? Because we need to know whether that original acid is weak or strong. To make it the original acid, you're going to add a hydrogen to it. So it becomes HBrO. Is this a strong or weak acid? Is it in our strong acid song? HNO3 and HBr. H2SO4. HCl, O2, O4, say high strong acids all. It's not in our strong acid song, so this is a weak acid. Follow the logic. A weak acid will have a stronger than water conjugate. When you have a stronger than water conjugate, you're going to write an equation where you have the conjugate plus water, and we work out the products. Our conjugate is BrO. So let's write out that the conjugate's stronger than water, so the conjugate, not the water, is going to set the pH. I'm going to sing some more of our pH song. If it's weaker than water conjugate, then pH equals 7. If it's a stronger than water conjugate, then Heiss, K, pH, and you're done. What is Heiss? Heiss is an equilibrium chart. The H stands for hydrolysis. That's telling you you have to add water to your compound. So let's write our Heiss chart. NaBrO, this is our salt. We're going to add water because we're making a Heiss chart. Let me write it HOH. Now since this, first of all, let's get rid of the metal because metals don't contribute to pH. Since this is a base, water will act as an acid. And what do acids do? They give protons to the base. So our products are HBrO, and we're left with OH minus from the water. Ice, what are our steps? Ice, K, solve, check, sun. Let's do our ice. Now what did they give us? They gave us the molarity, and that's what we need in all of these ice charts except for acid plus base. Let's write the in. Was 0.85 molarity. I'm going to cross out the water because solids and liquids don't belong in equilibrium charts or K expressions. And since they didn't give us starting concentrations of the products, we assume we're starting with nothing. The change, as always, we're going to let X equal the change. Since there's no coefficient here, there's no coefficient on the X. Subtract the X from the reactant, add the X to the products. And again, no coefficients here to put in front of our X's. So at equilibrium, we're left with 0.085 minus X for concentration of our BrO. We're left with X for HBrO and X for OH minus. Now, did they give us a K? think oh, here it is. They gave us a K for HBRO. That's 2.5 times 10 to the minus 5. So ice, K, solve, check, sun. We've done ice. We have to do K. But notice the K they give us is for the acid, HBRO. So we have to convert the K for the acid into the K for the base. So K for the base, we remember one of our handy formulas is 1 over K sub A. So we're going to take 1 divided by the K sub A, 2.5 times 10 to the minus 9th. So our K sub B is going to be 4.0 times 10 to the minus 24th. Getting crowded here, so I'm going to write our K sub B is 4.0 times 10 to the minus 24th. Our BRO concentration at equilibrium is 0.085 minus X. And our concentrations of HBRO and OH minus are equal to X. So now we can get rid of all of this. Ice, K, solve, check, sun. All right, well, we solved for the concentration of OH. These are our 3 compounds we're left with at equilibrium. Which one of these is going to set the pH? Well, that's a weak acid. That's a stronger than water conjugate base. That doesn't mean very much because, you know, water is water. So which one of these will set the pH? If whenever you see an OH minus or an H plus at equilibrium, they will always set the pH because they are the strongest base and the strongest acid. Since we have OH minus is equal to X, we can use our K sub B now to solve for the X. So our K sub B, ice K solve, 4.0 times 10 to the minus 24th. And I shouldn't have erased the chart. Our products were OH times HBRO, both of them X's. That's products on top, reactants on the bottom. Our reactant was BRO, because that was in our salt. Then we have 0.085 minus X. Again, you shouldn't have to use the quadratic formula in a final exam setting. So we're just going to assume we're going to eliminate the X subtracted from the original molarity because compared to the original molarity, it's very, very small. We're going to cross multiply. We're going to end up with X squared equals 4.0 times 10 to the minus 24th times 0.085. And again, to solve for the square root, we're going to take these two numbers, which when we multiply give us 3.40 times 10 to the minus 25. To find the square root, you're going to put 1 over whatever that exponent is, and that happens to be 2. And our answer is 5.83095,189 times 10 to the minus 13th. Well, now that we have the OH concentration, we move to our second memorized formula for pH, and that's POH equals minus log of OH. And when we plug this number in for OH, we end up with a POH of 12.23426,054. Our next memorized formula, pH, we don't want POH, we want pH. 14 minus this whole number. So our pH ends up being 1.76573946. Too many significant figures. Remember, only in a pH answer, only the numbers after the decimal are significant. So let's go back to our problem and find the number of significant figures that we have less of. Now I erased the other ones, but I'll tell you, our case of B only has 2 significant figures, so we're going to use the least number of significant figures in our answer. So our pH becomes 1.77. It's 1.77, here are our 2 numbers, because the number after our last significant figure, 5, is 5 or greater. So the 5 is rounding up the 7. So our pH of a salt, 1.77. Remember, acids, salts can make an acid, a neutral, or a basic pH bond. You can see really the only main difference for a salt is that if it's the salt contains a stronger than water conjugate, you have to add water and create that balanced equation at the top of your HICE chart, your hydrolysis chart. Okay, we'll see you in the next video.